Okay, this is another video in the series for Math 1073 for UTSA. We will be dealing with Module 2.1, which is on functions. So the first couple of examples are about determining whether or not a given relationship represents a function. So the way the notation is written for these ordered pairs, this means that A corresponds to B, it's paired with it, C corresponds to D, and A corresponds to C. So that like A is an input and B is an output in the first case, and C is an input and D is an output, and A is an input and C is an output. On a graph, this would be something like A is the x coordinate and B is the y coordinate. It's kind of like that, but we don't need to graph these when they have letters. It's just one thing is connected with the next thing. Okay. Now, this first example has a problem because the input A is paired up with two different outputs. So if we redrew this and went like, say, A and C as inputs would go to B, C, D as outputs, because I'm listing all three inputs, A and C. Well, one's repeated, but there's three inputs, but one's repeated. And then I'm listing the three outputs, okay, here, right? If I connect these with arrows, then A gets connected with B in this first connection. C gets connected to D in the second connection. And then A gets connected to C in this third connection. Okay. And the problem with that is that A as an input has two different outputs, and that's not allowed. So this is not a function. Why do we care about that? Well, it turns out that for doing algebra and calculus and various things, having relationships that are functions is not more useful, but easier to deal with. So most of you are going to take calculus at some point, and calculus on functions is significantly simpler than calculus on things that are not functions. So it's important to know how to identify when a relationship is a function or not. So you know, well, how am I going to deal with this? How hard is this going to be? If it's a function, that's reasonable. If it's not a function, that's harder. So it's important to be able to determine that difference. Anyway, let's go to part B. Now, I don't have to draw out the arrows like I did before. All I have to do is say, well, does each input only correspond to one output? So A only appears once as an input. B only appears once as an input, and C only appears once as an input. So none of the inputs have two outputs. You might notice that C appears twice as an output. That's actually okay. You to have a function, you can't have repeated inputs in your list giving different outputs, like this one over here in A. A appears twice as an input, and it has a different output each time, B and C respectively. That's why this is not a function. Over here, the inputs each appear once, and although an output is repeated, that's okay. So yeah, yes, this is a function. So I'll just write is a function. And all I'm doing is checking that none of the inputs has two outputs attached to it. Okay. So here we have an equation. Now, this is more like thinking about the graph of an equation. If you graph the equation, what will it look like? Will you have outputs? Will you have multiple outputs corresponding to one input? And what's implied here, and the problem doesn't quite say it, I don't think. What's implied here is by default, we typically will use x as the independent variable. I should probably change the size of my stylus here because it's getting a little blocky. So the independent variable is x. And the dependent variable is y. Okay, so if you were to say, oh, well, is there, I'm sorry, rather, are there any inputs that correspond to two outputs? Well, since x is the independent variable by default, I could say, well, can I pick two values of x? Or sorry, can I pick one value of x for which there are two values of y that correspond? If I solve this equation for y and get y by itself, I'll subtract 3x squared on both sides, get y equals 14 minus 3x squared. No matter what you pick for x, some number, you'll just have a total on the right. Y will equal something, right? If I pick 1, right? If x equals, say, 1, then y equals 11. And that's it. There's only one possibility, okay? And the difficulty here is you're not expected to check every number because you can't. There are infinitely many. There's no way to check all of them. But to recognize, you know what, no matter what I pick for x, there's only one result that I will get from squaring it and then times 3 and subtracting to 14. So I'm only going to get one result from this formula, okay? So this one I'll recognize is a function. And one way to think about it is, can you solve for y and get a formula on the right that only produces one thing at a time? In this case, yes, I have a quadratic expression. So this is a function. Okay. I'm expecting this one. I haven't looked yet. Right, now this one's different because over here, um, x is the squared variable, and over here, y is a squared variable. And again, for this course, we're going to assume by default that x is the independent variable, which I'll label IP this time, or IV rather, and then y is the dependent variable, dv. It's the output. Y is the output variable, x is the input variable. So if I try to solve for y and say, well, can I get the output variable written as a formula of the input variable? Well, I can subtract 2x on both sides. That's fine. Okay, so 6 minus 2x. Now, if I pick a number for x, well, let me back up. I'm sorry. If I try to solve for y, that's not so obvious what to do there necessarily. I can say, well, let me find the square root of both sides. Okay. Oh, oops. So the square root of y squared will be the square root of 6 minus 2x. And as we've probably talked about before, the square root of y squared is not y. Okay. This is not equal to y. It's more complicated. This is the absolute value of y, because when you square a number and then find its square root, the square root symbol means that what's called the principal square root. It always means the positive square root. So for example, if I were to start with -2, let's go off to the side here a bit. If I start with -2 and square it, I get 4, right? And if I find the square root of that, I get 2. So this minus sign does not survive the process. So when you square something and then find its square root, you don't get just that number back. You get the positive version of that number. And if the input was negative, well, the result is now positive. And if the input was positive, the result is now positive still. So that's why I say that the square root of y squared is not y. So we get the absolute value of y equals the square root of 6 minus 2x. And if I want, I can then say, well, we've talked about absolute values before. So if the absolute value of y equals the square root of 6 minus y squared, that means that y could be negative. Its absolute value is this formula. So that means that y equals plus or minus this formula. Okay, this is one way to see, oh, well, if I pick a number for x, like say 0, or let's say 1, if I pick 1 for x, right? Let's say x equals 1. Well, then I'm going to have y equals plus or minus the square root. Well, 6 minus 2, which is plus minus the square root of 4, so plus minus 2. Hey, I've gotten 2 values of y for that given x input value. That means this is not a function. There is another similar but different way to see this. If I just start by plugging in a number for x, like say, I don't know, x equals, I don't know, 5. I'll make up a number, 5. Okay, and I plug it in, so 10 equals, oh, maybe 5 is a bad choice. Yeah, 5 is a bad choice. Let me say x equals 2. Okay, so x equals 2. So a domain is something we'll talk about in a moment. Why doesn't 5 work? Well, we'll get to that. So if x is 2, then I have 4 plus y squared equals 6, right? Because 2 times 2 is 4. If I subtract 4 on both sides, y squared equals 2. So are there is there only one number that solves this equation? Well, no, there's two numbers, the square root of 2 and the negative square root of 2. So y equals plus or minus root 2. There are two numbers that solve this equation. So there are two outputs corresponding to this input. Okay, so I can either do algebra symbolically and get y by itself as a formula and then think about plugging in a number. Or I can start with, well, what if x is 2? What happens? And then see, well, do I get 2 or more outcomes as a result? Because if that happens, I have what's not a function. Or my conclusion is that this is not a function. Okay. So here, when you do this graphically, the idea is similar. Does each input correspond to exactly one output? So I can say, oh, well, when x is 4, right? Here's 4. Are there more than one output, or is there only one output? Well, on the graph, this corresponds to this point right here, and then also this point right here. So there are two outputs. Another way to frame this is what's called the vertical line test. If you can make a vertical line that hits the graph in two places or more, then this fails what's called the vertical line test, and this fails to be a function. And you can think about this as picking a particular x coordinate and then looking, oh, is at x equals 4, are there 2 points or is there only one? Or you can just pick a vertical line and just check the graph as a whole, more holistically. Just look at the whole thing. Is there a place where I can get 2 points rather than picking a number first? Okay. So I'm assuming F will pass that test. I don't know yet, but yeah, okay. So if I try to make a vertical line like this, right, then as far as I can tell from looking at the graph, what's shown, no matter where I put it, it only hits one place. Like this one hits right here, right? And no matter where I slide the graph around, the line rather, the line only hits the graph at one position. So this passes what's called the vertical line test. In fact, let's write that over here. Okay. This one passes, so this is a function. Okay. So when you have a relationship between inputs and outputs expressed with ordered pairs, then you're looking for, do I have an input that shows up twice with two different outputs? When you have an equation or formula representing a relationship, you're looking for, well, if I get the output variable by itself, if I solve for y, do I get a formula with one result at a time? And then with a graph, you can just resort to what's called the vertical line test. Is there a place to where now let me put this out. Maybe I was a little unclear. Finding one location where the vertical line only hits once is not sufficient. That means it hasn't failed yet. It has to be that you can move that line, and no matter where you move it, the line only hits once. And based on the way the graph is drawn, no matter where I move it, it only hits once. As soon as it fails that test and it hits twice somewhere, well, now it's not a function, which is what this one over here did. Okay. So let's look at evaluating functions, which we've done to some degree. I talked about plugging in a value here for x, which we've plugged values into equations, but I was talking about picking an x coordinate and plugging it in and seeing what the result was. That's basically picking an input value. Now, the notation down here is just different notation, but it's a similar concept. So what this right here means, oops, wrong tool there. F of 9. This is not multiplication. Some people will mistakenly see this as f times 9. And that's somewhat understandable because we use parentheses to indicate multiplication. If I have something like 2 parentheses x plus 1, this means 2 times x plus 1, right? The parentheses indicate grouping for a product. And you could distribute. Or if I have something like x plus 1 times x minus 3, right? I could FOIL that. The parentheses mean we're multiplying. But in this context, the context of function notation, this is not multiplication. You just have to get used to seeing it. This right here does not say f times x. This says f of x. Okay. And what that means is that we're finding out what is the value of the function at a given x value. So this means I need to take the 9 and plug it into the formula for x. So I'll have 9 squared minus 15. And of course, 9 squared is 81 minus 15. That is 66 would be the result. Okay. Over here, negative 9. I'm going to try to keep some of that on screen. Well, that's fine. I'll rewrite it up here. Okay, so now I'm going to find negative f of 9. Now, since I just found this, I know it's negative 66, but let's pretend that I didn't already have that. This I'm gonna intentionally do this incorrectly, and then I'll correct it. So this might look like negative 9 squared minus 15. That is incorrect. And the reason is this negation applies to the entire function result. So I need parentheses here. Okay. So this is negative 81 minus 15. So that's going to be negative 66, which is what we pointed out earlier. Okay. If I were to not have used these parentheses, then I would get the wrong result. Okay, what's next? Here, okay, so this might look a little strange because there are no numbers involved. This is something that will become important. This kind of thing where we have two components plugged into a function will become important in 1093 when we deal with trig functions, especially, well, reasonably early, but especially the second half of the course. This kind of thing will come up quite a bit. And then in calculus, this will come up a whole lot. So basically, what this says is I'm going to take this expression, a plus h, and plug it in for x into the function formula. So x will get replaced by a plus h. And this is not a squared plus h or a plus h squared, as in a plus an h with an exponent. This is the group a plus h squared. So this is equal to a plus h squared minus 15. Okay. Now, a really quite common error is to see this and go, oh, that's a squared plus h squared. Okay. Sorry. H squared. This is incorrect for a number of reasons. If you try to do this with numbers, it becomes pretty obvious. Oh, this doesn't work if you look at it numerically. So let's do an example of that. Let's say I did 2 plus 1 squared, right? If the exponent applied to each of those individually, well, then this would be 2 squared plus 1 squared, right? 2 squared is 4 plus 1 is 5, right? But of course, that's wrong because 2 plus 1 is 3. So 3 squared is 9, and of course, 9 and 5 are not equal. So somewhere in here, there's a mistake, right? And the mistake is that these two things are not equal, okay? 2 plus 1 in parentheses squared is not 2 squared plus 1 squared. It simply does not work. It kind of looks like a good idea. It makes a certain kind of sense, but it is simply incorrect. It just simply does not work. Okay. So what I need to do is basically FOIL. We talked about factoring previously. So a plus h times a plus h minus 15. So when I FOIL, I'll do a times a and a times h. So I'll have a squared plus ah, and then h times a and h times h. So plus ha plus h squared minus 15. Okay, I'm almost done here. When you multiply two numbers, the order in which you multiply doesn't matter. 2 times 3 equals 3 times 2. The term for this is that this is the commutative property, or we'll say that multiplication is commutative, or that multiplication has commutativity. So if you think about the word commute, it means to travel, to go to work, to go to school, right? Your morning commute, your evening commute. So it means to move, essentially. So you can move around the order of the product, and that doesn't affect the result. right? 2 times 3 is 6, just like 3 times 2 is. So here, a times h and h times a are the same thing. The order of the product doesn't matter. So I can take that second one, that ha, and I just noticed this spells aha. Maybe someone had a joke when they wrote up this document. Anyway, um, I will really have AH plus AH. So I can rewrite this as A squared plus 2AH plus H squared minus 15. Okay. So this is a little bit tedious, but this is what's intended with this expression, this function evaluation. And like I said before, we're going to need this kind of thing later. So this is a little bit complicated. This is something that shows up a lot in calculus. This is called the difference quotient. Um, so this is present in algebra for two main reasons. One, this is used to calculate average change over time, over a distance, for example. And then it's used again in calculus for a similar purpose. So we already worked out what f of a plus h is. So this is a squared plus 2ah plus h squared minus 15. So we already worked that out. But I have a big fraction. I'm just doing the first term so far. That might need to be longer. Yeah, let's go with that. Plenty of room. Minus, well, f of a. Okay, now f of a, all I'm going to do is take the original function and plug a in for x. So I'll have a squared minus 15. And again, I need parentheses. I need to group them together. I'm subtracting the entire group. So this is minus a squared minus 15. And again, much like with the previous example, I need these not previous, but a previous example. These parentheses are essential. I need them. Otherwise, I'm going to get the wrong result. And I'll see occasionally in Cal 1, someone will forget this, and they'll be doing a fairly complicated problem, and they'll make a relatively minor error at the beginning, and it just throws the whole thing off, and they're not even close to the right answer because they can't cancel the right things at the end, and they just kind of get stuck. So be careful about that. All over H. Okay. So now what I'm going to do is I'm going to distribute this minus sign onto this term and onto this term. So I'll have minus a squared plus 15. So big fraction, a squared plus 2ah plus h squared minus 15 minus a squared plus 15 all over h. And it might be obvious to you what has to come next. If not, pause the video and think about it for a second. What should we do next? So I'm looking at the 15s and notice, well, minus 15 plus 15, those go away, right? So let's cancel those. And then I notice I've got a squared and minus a squared. So those cancel out, right? And so I've got a fraction. I have 2ah plus h squared all over h, okay? And looking at this, something might come to mind as to, oh yeah, we can do this. A common error is to say, oh, these h's can cancel. But that doesn't work. It kind of looks like a good idea, but it does not work. If we examine this with numbers, it becomes obvious. So let's look at an example of that. So if I have something like, say, well, let's see. Let's say I've got 4 plus 8 over 4, something like that. Okay, let's say 6. No, let's say 4. Let's say 4. Okay. So if I go, oh, these can cancel, right? Then what do I have? Do I have 8 over 1? Does this become a 1 and this becomes a 0? Or is it 1 plus 8 over 1? Is that it? So this is 9, right? 9 over 1 is 9, but 8 plus 4 is 12 over 4. That's 3. And 3 and 9 are definitely not equal. So there's something here. And the something is that these 4s, they don't cancel. And you might say, no, well, you didn't put the right things here. Well, no, that's not it either. No matter what you put there, it's just, it doesn't work. Well, I don't want to say too much. If you put the right things there, I guess it would be equal. Put the 4s back, but other than that, no, there's just no way to make this work. This cancellation simply does not work. Okay, so here these h's don't cancel. Why is that? One way to say it is, well, this h right here is not available for cancellation because it's not a factor of the numerator. It's a factor within a term of the numerator. And in order to cancel out of the numerator with something in the denominator or vice versa, you have to factor the term you would like before you can cancel it. So in this numerator, I could recognize, well, you know what? There's an h here, and this term has two h's. So both terms have an h. So I could factor an h out of the top and say that I have h times 2a plus h all over h. And I just realized my h in the other denominator is not very good. There we go. Now these h's can cancel. Okay. And I'm left with 2a plus h. So this is the result of the difference quotient. It might not be very satisfying because we don't have a number, but there weren't really any numbers here. These are all, well, a and h are what are often called parameters. So it's somewhere between a number and a variable. This will become clear at a later time. For now, it's a number we don't know yet. And there's more than one kind. There are variables and there are parameters. Those are both numbers we don't know, but they're handled slightly differently. And especially later in calculus, you'll come to understand h a lot better as to what that is. Anyway, so that's that example. So part 3, solve g of x equals 2x plus 4 for the indicated values. Okay, so basically we're looking for, well, for what input would the function have an output of 7? So I'll just take this 2x plus 4 and replace it in there because that's what g of x is. So 2x plus 4 equals 7. I'll subtract 4 on both sides. So 2x equals 3. And I'll divide by 2 on both sides. So x equals 3 over 2. And that's it. I've found here is the input that causes the function g to produce 7 as an output. Next one, g of x equals negative 15. Okay, my function was 2x plus 4. So again, 2x plus 4 equals negative 15. So I will basically do the same steps, but you know what? I have options here, so I'm going to do something slightly different, just for it to look different from this. I move the 4 first in this case. I don't have to do that. I can move the 2 first if I factor the 2 out. So 2x plus 2 equals negative 15. Okay, I'll divide by 2, so x plus 2 equals, oh, forgot my equals there, equals negative 15. So this will be negative 15 over 2. I'm running short on room, so I'll start a new column. So now I'll subtract 2 on both sides. So x equals negative 15 over 2 minus, I'll write this as 2 over 1 in preparation for combining like terms and getting a common denominator. So negative 15 over 2 minus, this fraction needs to have a 2 on bottom, so I'm going to double the top and the bottom. So 4 over 2. So this is negative 19 over 2. So there's my value of x that causes that output value, negative 15. And I'll observe that this was a really roundabout way. It would have been easier and faster, I think, if I had just subtracted 4 on both sides and then divide by 2. I'm done in 2 steps. I just wanted to point out that there are 2 ways to do this, at least 2 ways. Maybe there's even another way. Anyway, so Part 4. Is there a part 5? No. Part 4. For the following exercises, determine if the following functions are one-to-one functions. What does that mean? A function is one-to-one when each output corresponds to exactly one input. Back when we talked about what makes something into a function, each input corresponds to exactly one output. That makes a function, the vertical line test. Now we're looking for what is a one-to-one function. That's where each output corresponds to exactly one input, the horizontal line test. So looking at this graph, this y coordinate say 1, right? Let me make my stylus even smaller since the graph is pretty small. This output of 1, right? Does it correspond to only one input? Yeah. It corresponds to the input -2. Okay. How about this? How about 0? This output of 0. Yeah, it corresponds to, I guess, -1 is its only input that corresponds to that output. And this amounts to what's called the horizontal line test. So if I make a horizontal line and I move it around, as long as it only ever hits the graph of the function at one position, no matter where I check, if I check every possible point and the graph is only touched once, this passes the horizontal line test. And this is what's called a one-to-one function. So these are the really nice functions where they pass the vertical line test in order to become functions, and then they pass the horizontal line test in order to become one-to-one. What that means is one-to-one, a one-to-one correspondence means that each input-output pair is unique, that the input -2 doesn't get paired with anything else, and the output -1 doesn't get paired with anything else. They each get just the one partner, basically. So this test, again, is called the horizontal line test. So this one passes because no matter where you put that horizontal line, this graph only gets touched once. So this is one-to-one. And this is going to be very important later in this course, as well as in pre-calculus. It shows up a lot. And it's important in Cal 1 and every other math class after that. With perhaps some exceptions, but pretty much all of them. This one, okay, now it is a function. It passes the vertical line test, right? If I make a vertical line and I move it around and I try to look for a place to touch twice, I can't find one. Every place touches just the once, right? But if I make a horizontal line, right away, there are 2 inputs that correspond to this output. So the output 3 has 2 corresponding inputs, which I guess I'll kind of approximate values. That's off a bit. That's better. So negative 0.4-ish. And then also, it's also off a bit. So what is that? 0.8. These 2 inputs share the same output. So this function is not one-to-one. This fails. This is not one-to-one. Okay. In fact, I should probably put this over here. Easier to read, not one-to-one. Okay, so that's basically some of the most basic facts about functions. How to identify what is and is not a function, and how to do some function evaluation. In the next module, we'll talk about some more features of functions.